The ellipse is our next conic section. You're going to be able to derive its equation given the foci and using the information that the sum of the distances from the foci is constant in an ellipse. The general equation for an ellipse is very similar to that of a circle, and in fact a circle, if you think about it, is a very special form of an ellipse where everything is the same distance from the center. In an ellipse, the distance from the center is going to change, and the more eccentric the ellipse is, the more that distance will change. But the general form for the equation of an ellipse is x over a, the quantity squared, plus y over b, the quantity squared, equals r squared. Very similar to the circle's equation. The only difference are these two new terms, a and b. Now, a stands for a number that represents the distance a point on the horizontal axis is from the center of the ellipse, assuming the ellipse is centered at the origin. So this distance from the center to a point on the outside along the horizontal axis is called a. So the points along the ellipse that lie on this horizontal axis are point a comma 0 and negative a comma 0. In a similar way, the number that b represents talks about how far up or down on the ellipse from the center that a point can be. So that distance b is the distance from the center of the ellipse either up or down to a point on the ellipse. So the points on the horizontal part of the ellipse would be the point 0b and 0, negative b. Now in all ellipses except a circle, one of them is going to be the bigger number. In this case, a is bigger than b. The red axis is larger than the green axis. You'll also see terms semi-major and semi-minor axis, and what that's referring to, semi of course means half, so the semi-major axis is either the distance b or a, whichever one's larger. In this case of a stretched out vertically ellipse, the b distance is longer. That's called the semi-major axis. The semi-minor axis is the smaller of the two, and it's the distance a in this case. It's always the smaller of the two numbers. They are also sometimes referred to as the semi-major and semi-minor radiuses or radii. By the way, you've probably figured it out, but if the semi-major and semi-minor axes are the same distance, we have a circle. So again, the circle is a very special form of an ellipse where a and b are exactly the same, so therefore we get x squared plus y squared equals r squared. Let's look at an ellipse that has the equation x over 5 the quantity squared plus y over 3 the quantity squared equals 1. But you're most likely not going to see it in this form. You'll most likely see it in this other form, x squared over 25 plus y squared over 9 equals 1. In which case the numbers 25 and 9 are not a and b. You have to take, they are a squared and b squared, so you're going to have to take the square roots to actually find them. So our semi-major axis, a, is going to be the square root of 25, or 5, which means that it's going to be along the horizontal axis because it's under the x. Semi-minor axis is going to be the square root of 9, or 3, and it's under the y, so it's going to be the semi-minor axis along the vertical axis. So to plot the ellipse, we plot the points 5, 0, and negative 5, 0 for our major axis, half of which is the semi-minor axis. And to plot the semi-minor axis, we're going to use the points 0, 3, and 0, negative 3. We're going to connect those, and that will be the graph of the ellipse. So if we want to shift this thing away from the center, we do it very much like the circle. And since the circle is a special case in an ellipse, this only makes sense. Let's suppose we wanted the center to be at 4, negative 2. In other words, we're shifting the ellipse 5 to the right and 2 down. So that we draw the center at 4, negative 2. And by the way, the equation looks like this. X minus 4, the quantity squared over 25, plus y plus 2, the quantity 9, equals 1. So we've got the center at 4, negative 2, because that's what makes this 0 and makes this 0. We see, again, this is the same ellipse as before, so a squared is 25, which makes a, the semi-major axis, 5. B squared is 9, so b, the semi-minor axis, is 3. So we're going to go to the right 5 and up 3 from the center, and then down 3 into the left 5 from the center to get our 4 points for the ellipse. So shifting 4 to the right and 2 down means an x minus 4. 4 to the right means a minus 4 here, and 2 down means a plus 2, y plus 2, so that when we put the coordinates of the center, 4 comma negative 2 in here, we get 0 plus 0, because obviously the center is 0 distance away from the center. So the equation of an ellipse is x minus whatever the horizontal shift is squared over a squared, y minus the vertical shift squared over b squared equals 1. So let's go back to the general equation for any conic section. And it has all of these terms in it, and that describes the entire plane that intersects the conic section. The ellipse is one special version of that, and we're going to include the circle in here now, because the circle we already said was this. So the ellipse is in the form ax squared plus cy squared plus dx plus ey plus f equals 0, where those capital letters are the coefficients of those terms. Another form that you're commonly going to see for an ellipse or a circle is the form x minus h squared over a squared plus y minus k squared over b squared equals 1. For a circle, a squared and b squared will be exactly the same, and in fact, they will be the radius squared. For an ellipse, a and b will be different, and the larger of the two will be the semi-major axis, the smaller will be the semi-minor axis. Final subject we're going to talk about is called the eccentricity of the ellipse. Looking at that word eccentricity, you see the word eccentric. So it really kind of shows you, eccentricity shows you how stretched out an ellipse is. And it represents a value from 0 to 1, with 0 being exactly a circle, and 1 a very, very stretched out ellipse. So to find the eccentricity of the ellipse, we also have to introduce a new term, and that's called the focus. And a focus in which there are two, both along the major axis. And from a focus, we can actually construct an ellipse from the two foci. Foci is the plural for focus. And the definition of a focus is a point on the major axis where the sum of the distances, and that would be these two black segments here, adding them up to any point on the ellipse, is constant. So I'm going to move this point F around along the ellipse. And if I were to ever add those two distances up, it would always be constant. And each of those is its own radius. It's the distance from the focus to that point on the ellipse. And the sum of those two radii must be constant. That focal distance is called C, and I've got that in orange here. And it's the same from the center to focus 1 as it is from the center to focus 2. That distance is called C. And the combination of C and the value of the semi-major axis will help determine the eccentricity. Now to find C, we use a very similar formula to the Pythagorean theorem, in that C squared is going to be the absolute value of a squared minus b squared. Now really what it is, it's going to be the semi-major axis squared minus the semi-minor axis squared, but if you put the absolute values around them, it takes care of both of them. So C would be the square root of that number, and that's the distance from the center to the foci. For our particular circle, A is 2, B is 3. Therefore, C squared is going to be 2 squared minus 3 squared, take the absolute value. So it's the absolute value of 4 minus 9, which is 5. That's C squared. C is actually the square root of that, the square root of 5. So the distance from the center to the foci in this case is the square root of 5. Now we calculate the eccentricity E by taking that focal length or focal distance C and dividing it by either A, in the case of A being the semi-major axis, or B in the case of B being the semi-major axis. In our case, because B is the semi-major axis, the eccentricity is equal to C divided by B, which is the square root of 5 divided by 3. That's approximately 0.745. Remember, if your eccentricity is always going to be between 0, which is a circle, to 1, which is a very eccentric ellipse. If you get a number that's not between the 0 and 1, you've made a mistake. So our circle is fairly eccentric with an eccentricity of 0.745. So we've looked in depth at the ellipse, how it's formed from the focus, the semi-major and semi-minor axes, and how they determine the equation of the ellipse. And we've also found its eccentricity by putting all of those things together.